In this video, we'll have a look at an approximation which is due to Fisher-Black in 1976 and which is based on the Black-Scholes option pricing formula. This approximation is often used to price various kinds of options, including interest rate options such as caps and swaptions. To begin with, just a reminder about T forward measures. Recall that the T forward measure, denoted QT, is the equivalent martingale measure for the zero coupon bond with maturity capital T as numeraire. In other words, the Radon-Nikodym derivative of QT with respect to the risk-neutral measure Q is given by this ratio of asset ratios, which you can easily see will simplify to the following. Notice here that the short rate R is stochastic. As a warm-up exercise, you can then show that the instantaneous forward rate is just the QT expectation of the short rate, and thus the instantaneous forward rate is a QT martingale. And similarly, you will be able to show that the forward LIBOR rate is a martingale with respect to the measure for its terminal date. I also want to remind you about the following formula for the log normal distribution. If x is log normally distributed, then the probability that x is greater or equal to some value k is given by nd minus, and the expectation of the positive part of x minus k is given by this expression over here, which looks a bit like the Black-Scholes option pricing formula, where d plus and minus take the following values. This formula is worth remembering. Let's now have a look at the Black 76 formula. This formula has long been the industry standard model used by traders to price a variety of European style options, including interest rate options such as caps, floors and swaptions. Consider a European call option C with strike K on some market variable X, which is observed at time T, but with the payoff received at a possibly later date T star. Here X need not be a traded instrument, it could be a market quoted rate, for example. In the case of caplets, for example, X would be the LIBOR rate, T would be the time at which we see the spot LIBOR rate, and T star would be the end of the period. In other words, T star would be equal to T plus delta T. The main assumption is that xt is log normally distributed in the risk-neutral world. We will make no other assumptions about the dynamics of x here. There is no dynamic hedging here. In other words, there is no arbitrage argument that leads to the Black 76 formula. We define the volatility of the random variable xt to be a non-negative number sigma satisfying the following equation. The variance of log xt is sigma squared times t. Now let Q be a risk-neutral measure. Then via risk-neutral valuation, we know that the call value is given by this expectation, where here R is the short rate, which may be stochastic. Notice again that the variable X is observed at time capital T, but the payoff associated with this call option is made at time T star, which might be equal to T or might be later. Now the Black 76 formula uses two approximations to determine the value of C0. The first approximation is discounting outside the risk-neutral expectation. In other words, we approximate the risk-neutral expectation here, which is the call price at t is equal to 0, as follows. And thus we have approximated the discount factor inside here, which is stochastic, by the value of the zero coupon bond. Now, because xt is assumed to be log normal under the risk-neutral measure Q, it follows that the Q expectation of the positive part of xt minus k is given by this formula here, where d plus and d minus are given by this expression here. Now notice that the Q expectation of xt occurs both here as well as in d plus and d minus. The second approximation approximates the Q expectation of xt by the T forward price or rate corresponding to that variable. Now, since the forward price of x at time t for time t is just itself, i.e. since ft is equal to xt, this can be interpreted as saying that the forward rate process has zero drift, i.e. that it is a risk-neutral martingale. The Black 76 formula for the call option is therefore given as follows. Here we discount outside the expectation, and we discount from time t star, which is the time at which the payment is made, and we use the forward price or rate instead of the risk-neutral expectation. Now let's consider Black's model applied to a caplet. The payoff of the caplet is given by the positive part of the LIBOR spot rate at time capital T minus the strike rate times delta T. But this payoff is made at time T plus delta T. So here T star is equal to T plus delta T. If we apply the above formula here, we obtain that the value of the caplet is approximately equal to the value of the zero coupon bond, discounting 2 times T star, with the LIBOR forward rate here, times delta T, where D plus and minus are given as follows, again with the LIBOR forward rate, and where sigma is a number so that sigma squared times T is equal to the variance of the log of the LIBOR spot rate, L, T, T, T plus delta T. Now let's assume that the LIBOR spot rate is log normal not under the risk neutral measure, but rather under the T plus delta T forward measure. Then by the change of numeraire invariant formula, we obtain the following value for the caplet. Here the denominator is equal to the value of the numeraire at time t plus delta t, which is equal to 1. The log normality assumption therefore yields the following value for the call, where here we have the expectation under the t plus delta t forward measure of the LIBOR spot rate. Now earlier I stated that it is an exercise to show that the LIBOR forward rates are martingales under the corresponding forward measure, and thus this expectation here is simply equal to the LIBOR forward rate at time 0 for the period from t to t plus delta t. This formula here is precisely the same as the one obtained by the Black 76 approximation, i.e. the Black 76 price is now exact without the need for approximation. Now in order to price a cap, i.e. a portfolio of caplets, it is therefore necessary to develop a model in which each LIBOR spot rate is log normal under its own corresponding forward measure. The log normal LIBOR market models will do just that, as we shall see. As an exercise, you will apply the Black 76 formula to a swaption, and you will then show that this approximation becomes exact if we assume that the swap rate is log normal not under the risk neutral measure, but under the equivalent martingale measure for the associated annuity.